Hello, everybody, and welcome to yet another contemporary math lesson. In this video, I will be going over section 9C, and we will be diving deeper into exponential modeling. And I'm hoping after you've seen the linear modeling episode or video that this tells you how we can use exponential functions in the real world. So not that long ago, we went over exponential growth and how it occurs when a quantity grows by the same percentage in each unit of time. Powertown began with a population of 10,000 people and grew each year by 5%. Began and initial mean the same thing here. With a 5% growth rate, the population at the end of the first year is 5% more than the initial value of the population, or 105%, which is 1.05 times the initial population. Remember the formula we have been using this whole time. The initial population times 1 plus the rate to the t power. And again, t can be months. In this case, it will be years, but the rate is going to be positive because it is, what does it say? Grew, it is increasing. So it's going to be plus there. More is another good word for that. And 5% would be represented as 0.05 as a decimal. So if you add 1 to 0.05, you can see where this 1.05 comes from. And what we can do is we can keep squaring or raising the exponent, increasing the exponents by 1. So 10,000 times 1.05 to the second power is 11,025. That's the population after 2 years. Population after 2 years. And the population after 3 years would be 11,576. And then we can just keep this going. After so many years, you can see that the exponent would match the number of years. And then we can just generalize to this expression right here. So let's see if we can use that expression up there to figure out this next question. Find the population of Powertown after t equals 40 years. So I don't want to keep multiplying over and over and over again. There was the population after 1 year multiplied by 1.05. We get this. The population after 2 years multiplied by 1.05. Get this. Here is the general formula, what I was just talking about, with our rate filled in already. So all we have to know is the initial population times 1.05, that's 1 plus the rate, raised to the 40th power because it's 40 years. And this is about 70,400 people. So let's see what happens here. Outside of the video, I did a little bit of math and I figured out the doubling time for this particular example. The actual doubling time here would be 14.2066991 to 7 decimal places years, doing it exactly and then taking a decimal approximation. So remember the doubling time we could approximate as 70 divided by the percentage. And the percent increase here is 5%. So when you divide these two numbers, you'll get 14 years. So this doubling time approximation of 70 divided by the percent is still pretty good. So if I raise the 1.05, let's do 10,000 times 1.05 to the 14th power, that is about 19,799 people. And that makes sense because I didn't go the full 14.2066991 years in my exponent. I didn't get quite to double. So it's nice to know that that still works out. And that this is still an approximation. That division that we can do, 70 divided by the percent increase, it's just an approximation, but it ends up being a pretty good one. All right, so the general form now of an exponential equation. The general form for an exponential equation is Q, or in the past we have used A, equals Q sub 0, or again in the past we've used P, is 1 plus R to the T power. So again, you can think of Q as A, and you can think of Q sub 0 as P. So this formula should be nothing too new for you. This is exactly the same and works exactly the same as the annual compound interest formula. So in this slide, we are going to see if we can use this formula to model some situations that can happen in the real world. Create a table showing the value of the quantity Q for the first 10 units of growth or decay. Make a graph of the exponential function. In our first scenario, we have the number of restaurants in a city that had 800 restaurants in 2013 increases at a rate of 3% per year. So what we can do then is we can already see it's given to us. And we can see in our description here that 800 is the initial amount. And this time we will call it Q sub 0. So to start out our equation, Q equals Q sub 0 1 plus R to the T power. And it's important to note that T will be in years. So we will have Q equals 800 times 1.03 to the T power. And that's because this is 0.03 as a decimal. So if we want to figure out how many restaurants were in the city after 1 year, we can replace T with 1. And with that, you'll be able to see there are 824 824 restaurants in the city. And we can continue doing this. We want to find out how many restaurants were in the city after 2 years. Well, we can substitute 2 in for T. And then we can see that there are 849 restaurants in the city. And we can do this for 3, and we can do this for 4, and we can do this for 5, and we can do this for 6, and so on, so on, so on. So there you have it. We have filled in all of these values by substituting the appropriate year in for T. Cool. Now we need to make a graph of all of these. And in order to make a graph of all of these, we are just going to have to rough it freehand here. So I'll make my X and Y axis over here. We know that years will be here, but the variable is time. And on the y-axis, we can have the number of restaurants. There we go. And since we know we're going to start at 800, we can put a little break in our graph and start at 800. And maybe we should just jump by 50 here. 900, 950, 1000, 1050. And I'm going to call myself out of space at that point. So 1 year, 2 year, 3 year, 4 year, 5 year, 1, 2, 3, 4, 5. Let's go out to maybe 6 years. That's fine. So at 0, I'm going to do the graph in bright green so that everybody can see it. So at 0 years, there were 800. After 1 year, there was about 824. 2 years, just under 850. 3 years, 874. About there. 4 years, we're at 900. 5 years, 927. And 6 years, we were at 955, so something right about there. And yeah, right at the beginning, this graph is growing pretty slowly. In fact, it almost looks like it's linear for most of it. But after that, after maybe 12 or 13 years, it would start increasing more and more and more and more, like this. All right, let's take a look. One more thing before I move on to the next one. You'll notice that every single time I had to round my values, the correct decimal value for after 4 years, how many restaurants, is 900.40 blah blah blah. We can't have a partial restaurant like this. So in all of these values, I simply round it to the nearest whole number. Oh good, looks like example 2, we get to talk about more drugs. Luckily, they are legal drugs in all of our scenarios. So a certain drug breaks down in the human body at a rate of 15% per hour. The initial amount of the drug in the bloodstream is 8 milligrams. So our Q sub 0 is 8 this time around, and milligrams. And we will still be using T, but T this time will be in hours. So our equation is Q equals Q sub 0, 1 plus R to the T power. There's one more thing I'm forgetting here. We want this breaks down at this percentage rate. Breaking down, disappearing, not effective anymore. This would be a negative 0.15 for the rate. So if we combine this negative 0.15 and 1, we will get 0.85 for our number inside the parentheses here. So the full equation would be Q equals 8 times 0.85 to the T power. Go ahead and see if you can fill in these results and round your numbers, the number of milligrams left, to the nearest hundredth, aka 2 decimal places. So here are the numbers I got, and before I go over that, we can graph this with the initial amount again being on the x-axis. So I'm just going to call this 8, jump up here, call this 8, and that it will be decreasing as time moves on. And I wanted to bring back just one last time here that 70, the rule of 70 here. We can take 70 and divide it by the percentage that we see in our example. Here is 15. Not only does this work for growth, it also works for decay. So if I take 70 and I divide it by the 15%, that is about 4.667 out to 3 decimal places. Sure. If we take a look then, how long does it take for 8 milligrams of the drug to turn into 4? Well, somewhere between 4 and 5. Well, yep, that is a number between 4 and 5 hours. It's 4.66. How long does it take for the drug to be cut in half twice? So the drug to be cut in half twice, we would have to go from 8 to 4. That's half of 8. And then half of 4 is 2. So when you look over here, between 8 and 9. So 2 half-lives, this number, yeah, it's getting a little off the more half-lives you go out, but it's still close enough. If we said it was 4, it would be pretty accurate here. Well, that's it. That concludes the lesson for section 9C, exponential modeling. I hope you learned a little bit more about how exponential functions work in this video. Good luck.